Good morning. I think we can start our session. Oh, I can. Okay, now I don't hear any feedback. Okay. Okay. Yes, you can. Thank you, Noah. Thank you for saying good morning. Then I know that you can hear me and you can see me. Okay, that's mean what we have. We have lesson 7. We have two sections. Related rates 2.8 and 2.9 linearization. That means we're still talking about some application of derivatives. Okay, and I believe next week we will have a spring break. Okay, that means we will have 1 week break. Of course, we have to take the break seriously, but then we have to have lots of energy, come back, and we will have 1 more week of instruction of a new material, and then we will have a midterm too. Okay, that means this week and 1 week after the spring break, we will have a new stuff, and then the second midterm. But we will still have like a midterm review, of course, and then the test. You may try to like book your appointment. I saw that most of you have already the appointment on Examity, but you can, if you don't have an appointment, you may try to book at your time slot, because like the last minute booking, it's not really, it's not good, because it's not many time slots are open, and then we're getting a little bit stressed, and we don't need this stress. Okay, that's what we have today. Related rates. What do you think? What we will talk about? And like just this topic, related rates, the subject, the title is telling you something, or just you just waiting for me to start? Yes, yeah, it will be word problems. Exactly. Of course, we will involve derivatives, but it's simply, I can say simply, just the word problems. Yeah. And we will have, like as always, we will have like a word, a scenario. We have to read carefully. Okay. We have to know what is given, what is required, and then we have to create some connection between given and required information, which means we have to create like an equation, most likely, and then solve the equation for unknown. And that's it. Yeah, that's the typical like algorithm to solve the word problems. But what will be special? The special thing will be, we will look for the rate of change. Okay, we will try to compute one rate of change with another one being like given to us. That means one rate of change will be given, and then we have to compute another one. Using different words, I can say that like something will be changing, some quantities will be changing, and with respect to that change, how the other related quantities are changing, which this will be the question we have to compute. Okay, that's pretty much, yeah, everything. That's me. Let's see what kind of question we may have. And let's, okay, yeah, that means just to compute the rate of change of one quantity in terms of the rate of change of another quantity. Yeah, we can do this. Okay, but before, one thing I would like to say, because we will have a problem, we will have a scenario, we will read, like we will probably draw some diagrams if it's helpful, we will label the picture, the diagram. But what is important is that we have to assume, unless it's obvious, but we have to assume that almost every quantity that we label is changing. Is a new function with respect to time. Okay? That means, for example, like, I don't know, let's say we will have a triangle. Okay, because we will have some, and I will just put A, B, and C. I have my picture, I have my labels. And I will say that the base A is changing. It's like increasing, increasing, increasing with some rate, okay? That means it's increasing with respect to time. And how can I indicate this rate? I can say rate of change or derivative of A with respect to time, dA dt. Yes, we remember dy dx. Yeah, that's mean, which we don't really like because I can still say A prime. Okay, that means the rate of change of A with respect to time, or I can even say speed or velocity. Yeah, more like, yes, more mathematically, physically saying. Okay, that means this, and now A is changing. And of course, looking at this triangle, when A is changing, we have to assume that B is changing. That means the rate of change of B with respect to time. Or we can say B prime, probably dB dt. If B is changing, then we have to assume that C is changing. Okay? The rate of change of C with respect to time. That means what is my point? My point is, whatever we will like, something will be given, but whatever we label, we have to assume that everything is changing. We can't assume that something is like fixed or constant, okay? Because then we will make the mistake. Because derivative of let's say x is different than derivative of the constant value, like 5. Yeah? Derivative of constant is 0. That means whatever quantities like x, y, I don't know, z, t, h, okay? Like whatever we will label, we have to like remember that we always have like a function behind this. That means derivative of x will be dx dt. Yes, we can see, because x is like just one of them. We will differentiate x with respect to time. We will differentiate y with respect to time, and so on. Differentiate z, t, maybe it's not a, let me just say, just to make a difference between the time. Derivative of the quantity t, of the function t, with respect to time. Derivative of h, maybe that's height, with respect to time. That means, please remember, we always have to remember that we have, behind each quantity, we have a function, and then that's the derivative, that's the rate of change, okay? All of this dx, dt, dy, dt, dz, dt, that's the rate of change. Okay, and please remember, do not assume that it's constant, unless it's obvious, and we will see, okay? We will see how this looks like. Okay, and I do have a steps, the procedure, okay? But you may pause the video, or we may like quickly scan it. It's just the same that I just typed all of the steps that we're taking, solving the word problems. We have to read the problems really carefully, draw the diagram, if it's of course possible, label everything, because like a naked diagram will be not helpful. Yes, we like some notations, X, Y, Z. We have to identify what is given to us, what is required to calculate, and then the known and the to be found quantities, we have to relate them. Yeah, because then we will be computing something, but some known information will be involved. And then we may connect, we may relate the quantities, but of course we will differentiate, because we will need the relation between the rates of change of these quantities. That means relate them, differentiate them, and then substitute whatever was given, and then get the final answer. Okay, and yes, you can see, but I will point out what I mean. The main error is that we trying to substitute, okay, number 7, we're trying to substitute some given information before the derivative. That's when we're trying to substitute and put to this model, equation, relationship. Okay? Which of course it will be wrong, because some of the quantities, they look like they are constant, fixed, but they are not. They still like, I don't know, increasing or decreasing. Okay, that we have to be careful. 0.5, 6, and 7. That's the order. Yeah, that means this is the typical mistake. But let's see. Yeah, that means let's just solve a few questions. Okay, few problems. Okay, I have example number 1. All of the problems I took from your textbook. Maybe I changed some numbers, or maybe even not. Or maybe I took directly. That means from your homework assignment or the textbook, they have the same question. Okay, air is being pumped into the spherical balloon so that its volume increases at the rate of 5 cubic centimeters per second. Yeah. Volume is increasing. And we can see volume with respect to time. Yeah, it's even the units are giving me the information that that's the rate of change of the volume because it's cube. How fast is the radius of the balloon increasing when the diameter is 20 centimeters? Okay, I don't know. I just draw the balloon, the spherical, yeah, the sphere, the spherical balloon. I don't know if we really need the diagram in this case, but it's nice to see. But what you even looking at this picture, we have to like imagine that is we pumping the air in and the volume is getting bigger and bigger and bigger. Of course, we can't overdo it, right? Okay, but we know that is increasing. Okay, that means if the volume is increasing, what do you think? It's the radius also increasing? Yes, yeah. Okay. What about, of course, because that's even the question. What about diameter? Is diameter increasing or diameter is 20? You see, that means this is kind of like the moment that we like you will, because of course we have to make some connection, relation, we have to make the equation, but please remember diameter is not 20. Yeah, that's what I mean. What this 20 means, like calculus. Yeah, calculus is like the rate of change at that instant. That means we're always calculating some derivatives, rate of change at one moment. That means this balloon is getting bigger and bigger, and at the moment when the diameter is 20, we have to find the rate of change. Yeah, that means this is the information, but diameter is not 20. Diameter is still, let's say, d, and it's changing with dt, the rate of change of diameter with respect to time. Yeah, that's please, yeah. But actually, diameter we will probably not involved. If the diameter is 20 at that one instant, what is radius? Can you tell me the value of radius? Because that's what we will, yes, that means this is a little bit, but the same thing, we will need that 10. But radius is not 10. We're just looking at the rate of change of radius at the moment that the radius is 10. Okay, that means given information and required information. Yeah, that's how we will start. What is given? Do you think you can, I did say that. Do you think you can type it for me? The rate of change of what? dv dt. Really nice, yes, but Yatniel also said rate of change of volume, yes. Okay, oh, and the relation. dv dt, really good, and we can see even the units are telling me v volume because it's cube. dv dt, it's given. What is required? Because how fast, of course, how fast is the speed or velocity, which means the rate of change of the distance. And the distance in this case is radius, thank you. dr dt. That means volume is given, the rate of change of the volume is given, the rate of change of the radius is required. But one thing, we're looking for the rate of change of the radius at the moment when the radius is 10. But radius is not really 10 for us. Do you remember like from the procedure, step 5, 6, and 7. 7, in the step 7, we will take that 10 and substitute, not at the beginning, okay? That means that's the only common like mistake that we're making. Otherwise, everything is nice and easy. Okay, That means in this case, how can I relate the given and the required information? Volume and the radius. This is probably the type of the question that we have to know that, yes, the volume formula. And if you will have this shape, which is not really complicated shape, but volume of the sphere, volume of the cone, maybe, we will give it to you. Okay, but if this question will involve like a cube, just like a box, probably you know. Do you know the volume of the box? Like just simply the box? Yes, of course. Length times width. That means this one. Yeah. Oh, yeah. Length times width times height. That's the volume. Yes, thank you. That means probably this one we will not provide, but we will provide the like some like rotate, like involving a circle, involving a pie. Okay. That means this is the formula, and we can see that means this is our step 6. We have the relation, no, step 5. Step 5, I'm just trying to 5, 6, and 7. We have the relation, but this is the relation between V and R. We have to differentiate, we have to get the relation between the rate of change. That means on the left-hand side, the rate of change of the volume will be dV dt, okay? 4/3 pi, that's constant. That means we will copy constant. And now, who can type for me what will be the rate of change or the derivative of r cube? We have to differentiate r cube. Do you think you can type it for me? I did type it. Okay, okay, Chuck, you can see you missing, yes. Oh, Yatniel also is missing something, but Noah has the right one. We have to follow our rules, 3r squared times dr dt, okay? Because of it's like a function behind. That means this is maybe the other part. Derivative of r cube, it's simply 3r squared dr dt. Okay, that means that's how we will always follow this, like a chain rule. Okay. Do you remember I mean, we can still say r prime, but that's the reason that I was using dy dx. And some of you were saying, oh, that's too much of writing y prime, it's easier. But that was one of the reasons, that because I knew it, that we will cover related rates. And it's nice to show the rate of change of the volume, of the radius, height, any other like scenario. Okay, that's when we have the relation, we have the derivative. Now we can substitute everything what is given. That means now you may notice I took that 10 and substitute, because now I'm looking for dr dt. The rate of change of volume is 5. I think I simplify. Did I simplify? I cancel out these 4 pi 10 squared dr dt. That means I have to take this 4 pi 10 squared and divide both sides of the equation. Okay, oh, maybe it's too fast. I did divide, and 10 squared is 100. And 100 divided by 5 is 20, 20 times 4 is 80, 80 pi. And units, we can always like copy, don't worry about the units, if they are of course the same, because we can see cubic centimeters and the radius is also in centimeters. That means now it's the distance over the time, which is distance was measured in centimeters and time was in second. Okay, okay, that's everything. That means identify what is given, required, relationship, derivative, substitution. Done. Yeah. But let's increase the level. That's the steps, and we have to just follow the same steps for every scenario. Let's look at the example number 2. Oh, 2. Okay. The ladder, 10 feet long, rests against the vertical wall. If the bottom of the ladder slides away from the wall at the rate 2 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall. Okay, that means you can probably imagine the scenario. We have a wall, vertical wall, we have a ground, and that's the ladder. Okay, and now, can you tell me that 10 feet, is this something that is changing, or is just something that I can use as a constant? It's a fixed, yes, yeah, because of course it's the ladder. That means the ladder is not going to be longer or shorter. No, it's 10. That means, yeah, this is, of course, some of the quantities, yeah, are definitely like fixed and we can use it. Okay, but we do have one quantity that is not, yeah, it's not fixed. Okay, that means this is 10 feet. And that distance, okay, the bottom of the ladder, that's the bottom. Okay, and the bottom is sliding, right? It's the dot is moving, let's say. Oh, I think I'm making the ladder longer, but we can say it's sliding down. That means on the vertical wall, the distance is decreasing, and on the bottom, it's simply like it will get 10 maximum. Okay, but we can say it's sliding down. Okay, that means this is the scenario. Do I have the picture? Yes, I have a nice picture. Okay, X, Y, and 10. We can see we can use 10. Okay, that means 2 feet per second. Can you tell me what is this like with respect to our labels? It's the rate of change of X or Y. If the bottom of the ladder slides away from the wall at the rate 2 feet per second, is, oh, I see X and I see Y in the chat box. The bottom, okay, that's we can see, we remember that dot. This, that means this distance is X, and then another X, another X. It's getting, okay, that means the bottom of the ladder slides away from the wall, because normally we will draw the ladder like this, right? It's like almost a vertical, and then it's sliding. That means that dot is moving. That means the distance from the wall is changing, which will be X prime. Of course, saying, using the Leibniz notation, dx dt, okay? That means this is dx dt is changing 2 feet per second. Probably quite fast. Okay, yes, the top. And the top, yes. Now what we have to find out, how fast is the top? That means how fast, oh, I have here eraser, how fast that dot is sliding down, dy dt. Oh, actually, yeah. And now, do you think, what color? I can maybe use blue. Do you think that 6 feet is a constant or is changing? It's a fixed number or it's actually changing? It's changing, it's a variable. Thank you. That's we remember, I will maybe use the blue color. We will use at the end, not in the original relation, okay? Okay, that means we have the rate of change of how the bottom is changing. We have to find out how y is changing, dy dt, at the moment, yeah, that the ladder is like 6 feet from the wall. Okay, now relationship, what do you think? We're seeing the nice right triangle and we're seeing labels, X, Y, and 10. The right triangle and each side is involved. What kind of relation we can use? Which of the mathematician we will bother? Of course, the Pitagoras, Pythagorean theorem. Of course, that means please remember that's the message, okay? If you see the right triangle and each side is involved and no angle is involved, because probably when some angles will be involved, then we will actually bother the trigonometric, yeah, ratio. But no angle, no, and each side is involved, then we have to use the Pythagorean. We have to. It's one of the easiest way. Okay, x squared plus y squared equals to 10 squared, and I can use 10. Okay, That's the relation between the quantities. Now we have to differentiate. And you will type for me, what's the derivative of x squared? Can you type it for me? Remember, x is another function. Yeah, x is changing with respect to time. That means what's the derivative of 2x dx dt? Really good. Oh, Kevin, yes. Okay, and respectively the same for y, y squared, dy dt. Yes, thank you. Dx dt, I mean 2x dx dt, 2y dy dt. Okay, and of course, 10 is constant, derivative of the constant is 0. Okay, that's quite good. Now we can substitute everything what we have. That means now I will take that 6 and substitute. Okay, I will definitely substitute because after the derivative, the rate of change of x is 2 feet per second. It's fine. We're looking for dy dt, but can you see we do have one extra problem? What quantity I will substitute instead of y? Yeah, that means this involves one extra step. I will put my 6 for x. I will put 2 instead of dx dt. Yes, that means we will use exactly the same relation. Yeah, can you see I just type it on the side? And at the moment when x is 6, we can easily calculate y. Okay, that means that's what we can do if we have multiple quantities, but each of them are connected to like in one diagram. Do you think what is y? Can you solve it for me? 100 minus 64, 36. Am I giving you the answer? 100 minus 36 is equal to 64, and square root of 64 is 8. Thank you. Okay, that's no, we do have 8. I even type this nicely. Okay, 2. What I did, I think I divide both sides by 2. When I divide equation by 2, 0 by 2 is still 0. Okay, because you can see my 2 is missing. The x is 6. I'm just trying to. Dx dt is 2, y is 8, and we're looking for dy dt. Okay? I divide each term, both sides of the equation by 2. Okay, that means now, can you calculate for me dy, what will be dy dt? We have 12, and we have to subtract 12 from both sides. Oh, okay. Dy dt, 12, subtracting 12 from both sides and dividing by 8, which will be negative 12 over 8. Negative 3 over 4, or over 2. Yeah, it's okay, it's just. Okay, that means this is, and it's still the distance, which is, in this case, the units were feet per second. And one question you can probably assume what I will be asking. Do you think the negative answer is correct answer? Or we did some calculation mistake? It is correct. And why is correct? Do you remember the rate of change when the rate of change is negative? Yeah, because it's decreasing. Yes, we remember when something is decreasing, we have lots of interpretation. The slope of it's negative. Yeah. That means the rate of change, when the rate of change is decreasing, it's negative. Okay, that means it's correct. 3/2. Yeah. It's rise over run, of course. It's the same idea. Yeah, the slope, because of course, slope of the line, slope of the tangent. Okay, let's solve few more. Okay, example number 3. What we have? 2 sides of a triangle are 4 meters and 5 meters in length. Okay, 4 and 5. and the angle between them is increasing at the rate 0.06 radians per second. Find the rate at which the area of the triangle is increasing when the angle between the sides of fixed length is pi over 3. That means at the moment, we have to find the rate of change of the area, how the area is changing at the moment when the angle is pi over 3, 60 degrees. 5 is hypotenuse. Okay, Kevin, you ask good question. We don't know if this is the right triangle. It's just the random triangle. Okay, that means maybe, but I can't assume because I don't, yes, I know it will be so nice to draw a right triangle, a little bit better, yes, relation, but no. We will actually, I can draw, because I didn't draw it. I will draw a random triangle, let's say, something that it's not suggesting that is. I will maybe draw the base 5, let's say 4, 5, and I don't know this one. Okay, that means this will be 5, this will be 4, and that's the angle between them. Yeah, looks good. I don't know. Maybe on the top we have 90, or I don't think we can. Do you think we can have a 90 degrees here if this is 60? Because this is 6, I mean, oh, no, I don't want to confuse you. At some point, this is 60. At some point, this is 60 because it's increasing. Okay, that means it could be tiny at the beginning. Yes, okay. But at some point, it is 60. That means we will not, because since theta is changing, okay, all of the angles will be changing. That means I will, it's not the information, it's not given. I will not assume that it's 90. Maybe at some point it's 90, but we will not look at these quantities because we have 4, we have 5, we have the angle. And I can draw probably the height because we will, it's not given, but we have to involve because the area. Okay, now the first question, because I did put 4 and 5. Do you think 4 and 5 are the fixed length and they will not change? Can I use 4 and 5? Yes. That means I don't have to label like A, B, or yes. And we can even see the fixed length, yeah, the sides of the fixed length. Okay, that means 4 and 5 is fine. But what about theta? Is theta pi over 3? Or is actually changing? It's like a function. It's the variable. It's increasing. Thank you. Okay, that means what is given? What given information we have? The rate of change of the 0.06 radians per second. Angle, the d theta dt. And of course, we're using radians, that's the measurement, the units for the angle. Okay, radians per second, 0.06 radians per second. And what we have to find out, find the rate at which the area, yes, dA dt. dA dt, thank you. And dA dt at the moment that the angle is 60 degrees, pi over 3. Okay, but let me use the blue. Please do not assume, yeah, this is not 60. At some point it's 60, but not for the relation. Okay, that means what we have, theta is given and A, area, is required. Would be nice to connect them, yeah, the relationship. Do we know any formula for the area of the triangle involving an angle between two sides? We do have formula like that, but I don't know if we know like right away. Yeah. Okay, of course, Kevin, you're right. I did type this. That's what we know. Relate, yes, okay, Matt, yes, okay, yeah, yes, you Yes, you guys, too good. Okay, but first of all, we will start with something. That means we all know the formula for the area of the triangle. 1/2 times base times height. Perfect. I don't know if I like the h, the height, because I have no information about height. Okay. What about b, the base? Do you think can I put and yes, and dA dt, of course. We don't, I mean, we're looking, Kevin, we're looking for dA for dt. That's mean we're looking for dA dt, which will be, yes, thank you, Yatniel. I don't know if I'm pronouncing correctly, but instead of b, I can definitely put 5. Then I have 1/2 times 5, because 5 is fixed. And h. And who said first? Math. And now, yes, now Noah is saying, yes, we have to relate h to theta. That's mean we have to rewrite h in terms of theta. That's mean now we will look at this nice triangle, okay, for h and this one, but I don't know what is that side. Yeah, I don't really know that side because it's not 1/2 of the 5, it's, I don't know. But what we have, I definitely know 4, I definitely have my h, I definitely have the right angle. Yeah, that's the good thing. And theta. That's what do you think? How can we relate theta and h using 4? Sine function? Because we have the opposite and the hypotenuse, h over 4, because that's definitely the good ratio, which means h is simply 4 times sine theta. And that's what I did. I did substitute. It means now we have probably 4 divided by 2. Look how nice relation we found, a and theta, yeah, on both sides. Yeah, but we did it. Through the additional relation, additional formulas, we have a nice formula. Yeah. Okay, now we have to differentiate because that's the relation between the quantities. We need the relation between the rates of change. That means on the left-hand side, nice and easy, and I think Kevin just typed it for us. Derivative of a is just dA dt. 10 is constant, but if you can type for me, if you can tell me what is the derivative of sine theta. But please remember, theta is another, it's a variable, another like function. It's cosine theta times, Kevin, you missing something? Yeah, like sine, like you remember, like we were using the u notation, sine of u. Derivative of sine of u is cosine of u times u prime. Yes, times d theta dt. Thank you. That means it's derivative of sine, it's cosine of the same angle, sine theta, cosine theta, times d theta dt. Okay. I think we can substitute everything. Right? Now I can take that blue quantity and we're looking for dA dt at the moment that the angle is 60 degrees. And I use fraction, just instead of 0.06, I put 6 over 100 because I think I can simplify 0 and 0. What is cosine of pi over 3? Do we know the unit circle? Cosine, it's 1/2, and 1/2, it will be 3 over 10. 3 over 10, which is 0.3. Oh, I can box it this one. But if you like, because it's I mean, we can still, because we don't have a calculators. That's mean I think fractions is always, we have nice numerators, denominators, we can cancel out quantities. We're not producing huge numbers, not even mention the decimals. Okay, that's mean 0.3. And yeah, That's the, and please note the units, because since it's the area, it's the square, the squared meters over there. Oh, Chuck, what do you mean just to understand? Yeah, I mean, I don't know exactly what you mean, but yes, we, okay. Okay, you probably hit the send. Yeah, sometimes that's happened when we typing a text and we would like to correct it and we hit the send, which, yeah, it's still, when the pi over 3, yes. Like at the moment when the angle is, because it's not changing in the, like, it's not a linear function, because we know when we have a line, it's changing, doesn't really matter at which point, it's always changing like at the constant rate. But when we have a different relation, like even parabola, yeah, at different point is changing with different rate. That's mean the same here. The relation is not linear, it's actually trigonometric. We can see that's the relation, which means depends on the angle. If angle is 60 degrees, the rate of change is 0.3. If the angle will be 45, we can compute, yes, we can compute square root of 2 over 2. Yeah. Yes, that's correct. Confirmation. Good. Because depends on the angle. Depends on the moment. Like, you know, we can compute the derivatives. We can have the formula for the derivative, like even the derivative of x squared is 2x. If x is 5, the derivative is 10. The rate of change is 10. If x is 50, the derivative is 100, 2 times 50. Yeah? Depends on at the moment, it's different rate of change, different slope. Okay. Let's maybe solve one more. I have lots of problems, but I will provide the solution, because I don't want you to, like, yes, to overdo it. Yeah. As I said, I wish you will do the calculus from the entire day, but of course we still have to have some break. Let's solve one more, and maybe I can start tomorrow the session with one question, or you may bring some question that is bothering you, like maybe the homework question, and then we will do the other section, which is linearization for this lesson. Okay, let's solve one more. Okay, let's do this one. Let's do this one. A plane flies horizontally at the altitude of 5 kilometers. Okay. And passes directly over the tracking telescope on the ground. When the angle of elevation is pi over 3, this angle, the same angle, is decreasing at the rate pi over 6 radians per minute. How fast is the plane traveling at that time? Okay, that's what we have. We have a ground, we have a telescope, and the plane is flying, right? That's the plane. I think that's what, but at the moment here, okay, that's the moment that we can track. Yeah, and the height, actually the altitude, the good thing is we don't have any like angles. That means the plane is flying horizontally, and 5 is of course fixed. Okay, but at this moment, that line of sight, this one and the ground, that's the angle of elevation. Yeah, like you can imagine that you are on the ground and you see directly above you the plane. Yeah, that means it's like 90 degrees. And then of course you're trying to keep the track with your eyes, the track of the plane, but the plane is getting, of course, away from you, away from us. It's getting further and further, and eventually, that means that's the angle of elevation. Yeah, it's getting smaller and smaller and smaller. It's decreasing. From 90 degrees, it's getting, that means the angle of elevation will be the one side initial side of the angle will be the ground, and the other will be like the line of sight, or you can say my arm, yeah, like the ground. Yeah, makes sense? Yeah. Okay, but I will remove this and I will just draw the one moment. Given, required. Oh, I think I didn't draw it again. That means this is the ground. That's the oh, no, wrong. That's the telescope. But we can see, oh, no, that's the plane. Okay, and this is the angle of elevation, and this is 5. Okay, we know the scenario before. Okay, oh, one thing I can maybe messed up. Okay, the plane, yeah, the plane is traveling, flying, because I have to label the distance that the plane is like it's making, because what is the question? The question is how fast is the plane traveling. How fast means the speed, the velocity. And this is distance over the time. That means how the distance behind the plane is changing with respect to time. And this is the moment that I start tracking. That means, let's say the plane is here and then the plane is here. That means this is the distance, and the plane is here, this is the distance. The plane is here, this is the distance. That means distance behind the plane, which I can project this on the ground, and I can label that part, yes, of that side of the triangle as a x, as a distance, and we're looking for the x dt. Okay. Yeah, that means x, which of course is the distance behind the plane, how this distance is changing. Okay, that means how fast. That means, okay, sine theta, we will definitely need some, Okay, that means let's see, given information is decreasing on the angle of the elevation. That means how the angle is changing, d theta dt. Oh, can you see negative sign? And do you agree with this negative? Okay, that's, yeah. Do you see? Because of the, okay, I would like to make sure, because this is telling me, that means you can see sometimes we may have the word decreasing, and we have to remember that it's negative. Okay, decreasing. Okay, now we're looking for dx dt. Okay, we know, like, because we're looking how fast the plane, and always the speed is the distance, like behind the object. Yeah, like the distance that we passed, how the distance behind the object is changing. Dx dt at the moment that the angle is pi over 3, but we know the angle is not pi over 3. Angle is angle theta. Yeah, this we will take after. Yes, that means we will try, yes, we have to make the relation. And now, yes, okay, now we have a right triangle, we have theta, we have the opposite side and the adjacent side. No information about hypotenuse, which Pythagorean theorem will be not an option, probably, because we don't want to involve another quantity which we have no information about. Okay, that's we have x, 5, and theta. What relation? I see that Kevin said tangent. Do you agree? I think we can, because we have opposite and opposite and adjacent. Okay, that means we have to just make the relation between theta and x. Theta and x. Okay, that means I can maybe write tangent theta. It will be 5 over x. I think looks good, but what is the next step? Because I would like to give you some small hint. What is the next step? If I have the relation, what we will do? We have to differentiate. Derivative, thank you. Derivative. That's we can definitely differentiate tangent, no problem. But let's look on the right-hand side. 5 over x. X is in the denominator. That means this is x taken to the power of -1, and then we have to use. But what do you think? Do we have, yes, that's what I was. We may use another relation. Like instead of 5 over x, I can make x over 5. That means what function? I can see. Thank you, Yatniel. It's cotangent. Yeah. Because what is the derivative? Can you tell me what's the derivative of x over 5? Like 1/5 x. What's the derivative? It's just 1/5. Of course, we still have to remember about dx dt. Okay? But that's always the case. That means this is just x to the power of 1. It's just the constant 1/5. Differentiating this, we will have few extra steps. It's still possible. It's still possible, but it's just less complicated. Okay, Matt is asking, oh yeah, we will take care of the right-hand side. I mean the left-hand side. Differentiating cotangent or tangent, I'm assuming it's similar. We have to just know the formulas. I'm just trying to explain the difference in the easiness. Yeah. Right, but it's not memory. Oh, no. We have to know the derivatives for. Did we have trigonometric function? We did have trigonometric function. Oh yeah, no. We have to know derivative of sine, cosine, tangent, cotangent, secant, cosecant. Oh yes, because later we will have the integration. We have to. Okay, I know. You can always rewrite quickly cotangent as a cosine over sine and do the quotient rule. Yes, that's the formula. Math, yeah, if you know derivative of sine, derivative of cosine, and cotangent is cosine over sine. That means maybe 2 minutes longer. You can do the quotient rule. Yeah, yes, yeah, that's what I did in the section 2.4. You can check that. Yeah, but since we're using a lot and we have to focus on different things, it's worth to remember. Okay, but that was my point. To instead of that, means please always, if you have to like debate between tangent and cotangent, think which ratio is better. Keep the x on the top. It's always the linear. Okay, that's me now derivative. Oh, I did rewrite. It's okay. I just multiply by 5. Okay, derivative of x, dx dt, 5 is constant. Derivative of cotangent, theta is negative cosecant square theta, d theta dt. Let me erase this. Okay, and now we can substitute everything what we have. Cosecant is 1 over sine. That means, let's see what I did. Looks a little bit crazy, but I think it's cosecant square. That means I have cosecant square, but cosecant is 1 over sine, and I did substitute pi over 3 now. The rate of change of the angle is negative pi over 6. And please notice that that negative is not squared. Yeah, that negative is not squared. That means I kept outside. Okay, negative and negative will give me positive. Okay, unit circle, sine of pi over 3. Do you know that value? Sine at pi over 3, sine at 60 degrees. We may remember square root of 3 over 2, or you may use the special triangle. Also, it's up to you. Yeah, square root of 3 over 2, but I flip that value because it's in the denominator. Yeah, that means square root of 3 over 2, and I flip it, and then I square 2, which is 4. 4 times 5 is, oh no, something wrong. I mean, it is correct, probably I simplify. 5 times 4, square root of 3 squared is 3, and pi over 6. Okay, that means it's 20 over 18. Dividing by 10, we have 10 over 9. Pi, of course, and kilometers per minute. Okay, that means this is actually the speed of the plane. I think the units are a little bit crazy. And the number is still including pi. That means I'm assuming this number has the reasonable speed because the plane has to have some certain speed, yeah, in order to be up and to move it. Right? That means we can probably multiply 10 times 3.14 divided by 9 and changing maybe kilometers per hour or miles per hour, then we will feel it. But I'm assuming that the answer makes sense, is definitely positive, and I think we didn't make any calculation mistakes. Okay, that's been on this slide. On this question, I wanted to point that always check cotangent versus tangent. Okay, and as I said, I have a few more questions. You can check. I will post these slides on Canvas as always. That means you can check. And if you like some of the questions, please tell me tomorrow during the evening session, and I can start the session with solving one of these questions. Okay, that means please solve your homework assignments question. Please even solve these questions again, and you will have no problem with your weekly quizzes and of course the midterm, which we will have